On numbers 1 through 10 on your study guide, it tells you that you will be given 8 true-false questions on your test based on these terms and relationships that we've learned about points of concurrency. So you need to remember what the point of concurrency is called for the given segments of the triangle. So one thing that we've talked about is that if your segment starts with a vowel, you know your point of concurrency is going to start with a vowel. Well, it's not a perfect system because we have 2 points of concurrency that start with a vowel, the in-center and the orthocenter. So you're going to have to remember that angle bisectors intersect at the in-center. The other vowel is altitudes. They're the ones that intersect at the orthocenter. And then the 2 that start with a consonant have the point of concurrency that start with a consonant. So we have 2 of those as well. We have the circumcenter and the centroid. So the medians intersect at the centroid, and the perpendicular bisectors intersect at the circumcenter. So that's just the terminology, the matching of the segment with its point of concurrency. So make sure you have that straight on which ones go with which. Then we have to know the relationships that are formed. And so number 5 says the in-center of a triangle is equidistant from the what of the triangle. So remember, the in-center is the center of what we would call the inscribed circle. Inscribed circle is the biggest circle that is inside the triangle. So the center of that circle is the in-center of the triangle. Remember that all radii of a circle are congruent. So if I connect that center to each one of these points that we touch the sides of the triangle with, then all of those distances have to be congruent to each other, which means the in-center is equidistant from the sides of the triangle. The circumcenter of a triangle is the center of the circumscribed circle. So I'm sure I will not draw this very well, but this circle goes through all 3 vertices of the triangle. So the circumcenter is the center of that circle. Again, all radii are congruent. So if I draw a segment from the center to each one of those points on the circle, all of those will be the same distance, meaning that the circumcenter is equidistant from the 3 vertices. So you need to know which one is equidistant from the sides and which one is equidistant from the vertices. Remember that the centroid is where all the medians intersect in a triangle. When we have the centroid, it's separating the median into a ratio of 2 to 1 or 1 to 2, whichever way you want to look at it. The longer part is twice as long as the shorter part. So if you remember when we were doing partitioning of a segment, when we would want to say how far that point is across the entire segment, we would write it as a fraction. We would do part over whole. And so if we do part over whole here, we would have the 2 as the part and the sum of 2 and 1 as the whole, meaning that the centroid is 2/3 of that entire distance from the vertex to the midpoint of the opposite side. So that's the fraction you're looking at there. That point is 2/3 of the way across that entire distance from the vertex to the midpoint, not 1/2. If it was 1/2, then each one of those parts would be congruent to each other. It's 2/3. Number 8 and 9 are using exactly what you were talking about on 5 and 6. If you want to inscribe a circle, and it should say really in a triangle. If you want to inscribe a circle in a triangle, then you would use the in-center to do so. In-center is the center of the inscribed triangle. If you want to circumscribe a circle about a triangle, then you would have to use the circumcenter. And then the last relationships that you need to know here are you're writing whether the point of concurrency is inside, outside, or on the triangle. For an acute triangle, every single one of your points of concurrency will be inside the triangle. Always for an acute triangle. you also have 2 points of concurrency that are always inside, regardless of what type of triangle you have. And those are the incenter and the centroid. And that's because when you do an angle bisector, when you're bisecting that angle, of course that segment has to be inside the triangle. Same thing when you're going from a vertex to a midpoint. That can only be done inside the triangle. So these 2 points of concurrency, it doesn't matter what type of triangle you have, those points are always going to be inside the triangle. The only 2 that can be on or outside are the 2 that have that perpendicular or right angle relationship. So a circumcenter, remember, is created from the perpendicular bisectors. If you have a right triangle, it's going to be on the triangle. In fact, it's going to be the midpoint of the hypotenuse of that right triangle. If it's an obtuse triangle, it's going to be outside the triangle. The orthocenter, remember, is from the altitudes. So if you have a right triangle, 2 of your altitudes are sides of that triangle. So those are intersecting right at that vertex. The third one would start from that vertex and be perpendicular to the opposite side. So all 3 of your altitudes are intersecting at this orthocenter, which is on the triangle, and more specifically, it's the vertex of your right angle. And then just like the perpendicular bisectors, the altitudes can go outside when you have obtuse triangles, so the orthocenter can be outside the triangle. So again, you're going to have a lot of true-false questions based on these terms and relationships. So for instance, if I said that the orthocenter is the point of concurrency for the medians of a triangle, that would be false. It's not the orthocenter, it's the centroid that is the center of the point of concurrency for medians. If I said the centroid is 1/2 of the distance from the vertex to the midpoint, that would be false. You would correct it with 2/3. If I said that in an obtuse triangle, all of your points of concurrency have to be inside the triangle, that would be false because we have 2 that can be outside the triangle. So you need to know all of these relationships so when you are given those true-false questions, you know how to answer them. Now there are 2 additional properties that I want to remind you of that might come up in your true-false questions. One is for the isosceles triangle, and one is for the equilateral triangle. So remember, with an isosceles triangle, from the vertex angle only, when you draw one of those segments, you're drawing all 4 of those segments. So if this was a median, it would also be an altitude, a perpendicular bisector, and an angle bisector all at the same time. That's not true from the other 2 angles, so you wouldn't have your points of concurrency all at the same point, but they would all have to be on this line. With an equilateral triangle, from any of the vertices, when you draw one of the segments, you're drawing all 4 of those segments. And that's true from all 3 of the vertices, which would mean your orthocenter, your incenter, centroid, and circumcenter would be all at the same exact point. So all at the same point here, but not here. They would all be on that line. Remember, that's called Euler's line. It's spelled, it looks like it would be pronounced Euler, but it's Euler's line.